Okay, so let's move into looking at our first problem for chi-square. We're going to take a critical value approach to solving this problem and connecting it back with some of the different examples we were discussing we use the chi-square for. What you're looking at here is we're looking to assess whether or not data has actually been measured versus recorded. So what we're looking here is practice problem number 6 on page 544. We've told we have a random sample of 100 people from California. And the questions we have to assess are the heights actually measured or were they reported. We know that when people report, for example, their heights or their weights or other characteristics like that, they tend to round to the nearest 5. So we tend to get higher rates of zeros and 5s in data that has been reported rather than with data that has been measured. If data has been measured for heights, weights, some other medical aspects that we look at, we find that the last digits all occur with the same frequency, 0 all the way through 9. So this is what we're going to be looking for, is checking and seeing, is this data actually accurately collected before I begin to do any of my analyses with it. Because of course, if it hasn't been accurately collected, any analysis I have will be fundamentally flawed due to the research design. So this is where we use stats to help check research design data collection. And in fact, when you're hearing about people building large survey sets of data for thousands and thousands of people to be able to produce a distribution, this is basically what they're talking about, is trying to produce a known distribution. What do we see when this data is collected appropriately? And then once you have that pattern of frequency of digits, you can apply that same pattern to later data that's collected to check it and make sure it was collected accurately. So here we're going to be using a significance level of 0.05, and we're going to be testing the claim that this sample is from a population in which the last digits do not occur with the same frequency. So that's the challenge we have that we're going to be looking at. So, and that would mean that they were reported, not measured, and that is not what I want for my analyses. I want measured data. So what's going to be my first step here? What's the first step for any analysis before you move into your numbers or anything else or even your hypotheses? You need to first be checking your requirements. Now we have 3 specific requirements here for chi-square analysis. What are those 3 requirements? Well, we're going to need to have a random sample, as always, right? We need to have a sample data that consists of frequency counts for each of the different categories, all right? And for each of the expected frequencies, the value has to be at least 5. All right, so here are our criteria that we're working with. This is the requirements for doing a chi-square analysis. Notice these are very different from the requirements we've used previously. And what usual requirement is missing from this list? Well, usually we've worked with having to have either an n greater than 30 or samples from a population with a normal distribution. So in this case, we don't have to have either of these. This is where chi-square allows me to analyze data that otherwise I would not be able to apply a t-test or other parametric analyses to. So that's why it's very important for using, especially again in real world situations where if I only have so many people that are coming in using services, I can't actually go to recruit more. I need to be assessing whatever I actually have to work with. So here we're looking at checking our requirements. Let's go through and compare this with the data that we have for this problem. So we can see if we go through and look at this, does this data meet the requirements for conducting a chi-square analysis? And yes, it does. So we have frequency counts for each of the different categories. As we can see, and we'll see in a moment, for each of the categories, the expected frequency is going to be at least 5. So we'll be looking at that in just a moment. Okay, so we got our requirements, and we need to identify the specific claim or hypothesis is to be tested. Right, so it's our next step. We're looking at that one. Now, again, here, so we're looking pretty much at developing our null hypotheses. We have to think through this differently than we have for our other problems. So here's what we have to look at is, for the null hypothesis, would maintain that it matches the expected frequencies. So when you're setting your null, this means that I'm saying that my sample data matches the previously established expected frequencies. So the frequency counts agree with the original claimed distribution, and my alternative is going to be the frequency counts do not agree with that original claimed distribution. So these are the two different things that we're looking at here. And again, if you find the language that I have in the text a little confusing, you may want to include into your notes this paraphrasing that I've provided, which is basically the null says that the data matches with the expected frequencies, and the alternative says it does not match with the expected frequencies. So that shorter version may be helpful for you as well. Okay, this is why this study is called a goodness of fit study, because here's my expected frequencies. Does this fit well with my expected frequencies, or does it not? So that's when you have the name goodness of fit. This is where it comes from, is assessing the match with the expected frequencies. So now we need to figure out how we determine the expected frequencies. So that's our step before we go further forward. So let's think our way through this. To kind of do this, let's start with a simple example, and then we're going to go back and apply these principles to our current problem. So what is the expected number of girls born in 100 births? So stop and think about that. What is the expected number of girls born in 100 births? All right, and how did you determine this? What was the thought process you used to determine the expected number of girls born in 100 births? Well, you probably used something like this. So you would take the total number of births, we have 100, right? Divided by the number of genders possible. We have two possible genders here, and what is arguably a simplistic version of the genders at birth, but we will leave all those complexities to the side for the statistical problem. So we'd have 100 divided by 2, which gives us 50. Okay, so that's one way we could have solved it. The other way we could, so if we're looking at this one, we can use this approach and we expect all the possible outcomes to have an equal probability of occurring. So if I expect all of them to have an equal likelihood of occurring for each of the possible categories, I can use this approach here. However, the other way we could have solved it is taken the number of births and multiplied it by the probability of girls. So the probability of giving birth to a baby girl is 0.50. So 100 times 0.50 gives me 50 as well. So multiplying the total sample size by the probability of a particular outcome is another way of calculating the expected frequencies, right? And we use this approach if we have a different rate of probability for two or more of the outcomes. So depending upon the problem and what we're working with, we're going to use one or the other of these two approaches to determine the expected frequency. Now, both of these approaches match up with the formulas your book has provided. So if we're looking at the expected frequency, you have n divided by k. In this particular formula, k represents what? So the k is going to be representing your number of categories, right? So if we're looking at the second one, where the expected value equals n times p, p represents what? And p represents my probabilities that we've been working with. So here we have got n divided by k, that's the number of the different categories. So if you look at this, you can see that the intuitive approach you used to solve this problem that I gave you is actually what's specified out here more formally in the formulas that we're using. Okay, so keep this in mind for when you're working on these problems. Calculating the expected frequencies appropriately is a critical part of getting the problem correct. If you get your expected frequencies incorrect, your solutions are going to be incorrect. Okay, so if this is true, right, if they're measured and they all have the same frequency of the last digits, then what are we going to be expecting in terms of our probability for each one of these options, right? So what would we be expecting to see? Well, we'd be expecting all of them to be equal to each other, okay? So, because if they're occurring with the same frequency, all of them are going to have the same probability, so they're also all going to have the same expected frequencies. Okay, so then that's what we're looking for our HO, okay, our null. So if it's reported, right, so this is the thing that we're challenging, we'd have higher rates of 0 and 5. So in this particular case, we don't actually need to specify the higher rates of 0 and 5. We can actually just write this out as at least one of the probabilities is different from the others, okay? So we can simplify that and not have to specify the 0s or 5s. We can simply say that we're expecting at least one of the probabilities to be different from the others. So that's going to give me, now we have both null and the alternative that we've got set. And here we have them set up in our hypotheses formula. And so now looking at the critical value approach, what's going to be my next step here? Well, we're going to need to identify the specified alpha. So what's going to be my alpha for this problem? The alpha is going to be 0.05, since again, alpha and significance level the same thing. And then what's my next step? Well, I've got to identify my relevant test statistic. So there's a couple of different, and here we're going to be working with the chi-square, and this is the symbol that we have here. So the cursive large X with the 2 over it. So that's the chi-squared symbol. All right, now we move on from there, and we need to calculate our test statistic. So we can calculate the test statistic using this particular formula here, okay, where we have the observed frequency, and we subtract the expected frequency from it and square that, and then divide it by the expected frequency. And once we've done that for each of these different categories that we have, then we sum all of that together. So that is one way that we can solve the problem. The other way we can solve the problem is using StatsCrunch. So if we're going to be going in using StatsCrunch, you're going to open this up. Now the first thing is we have to enter in our data, both our observed, and we have to calculate our expected before we can go any further. Okay, so since we have StatsCrunch, here we have our observed data. Notice that matches up with the frequency we have here at the bottom. And the next thing we have to do is we need to calculate out what is going to be our expected value. So if we go and look at our problem here, we can see that if our null is true, so if it's measured, right, then we would expect the same frequency of all last digits. So that means we're going to use this approach of n divided by k. So in this particular example, we're going to have a random sample of 100. We're going to divide it by the number of categories we have. How many categories do we have in this problem? Well, we have 10 categories, 0 through 9. So each of those is a separate category. So I'm going to take n divided by k is going to give me 100 divided by 10, which is going to give me an expected value for each of these digits of 10. So once you enter that in for your expected values, right, and go through these steps, so you're going to be opening up, once you've got that set up, you're going to open up stat, goodness of fit, because remember that's the type of test that chi-square is, then a chi-square, you're going to select your columns appropriately. When you run your analyses, you can output something like this. You notice, first of all, here on the bottom part, you should be able to see your observed data and your expected. So here we can see that set up. And then we can also see the output here. So there's my chi-square value, which is my chi-squared obtained, right? So that's 6.6. And notice this also gives me, by the way, my p-value. That we'll come back and look at that with a different problem. So now I have my chi-squared is 6.6. Now pay careful attention. The rounding rule here for chi-square is always going to be 3 decimal places. That is because if you look at your chi-square table, which we're going to look at in just a moment, your chi-square distribution table, you're going to see that those also go out to 3 decimal places. So make sure you're rounding appropriately for your calculated test statistic. So now I'm finding, the next step is, of course, as I just hinted at, is finding our critical value. So if I'm going to go find the critical value, we need to take a moment here and kind of step over and look at the chi-square distribution to help think about how that affects using the chi-square distribution table. So the chi-square distribution is not symmetrical. So unlike the normal distribution or the t-distribution, it is not as symmetric as you can see here on the left figure. So as the degrees of freedom of the distribution becomes more increases, it does become more symmetrical. So you can see the comparison over here on the right of the chi-square distribution for degrees of freedom of 10 as compared to degrees of freedom of 20. So it has, as it gets larger, we have larger degrees of freedom, it approaches a normal distribution. Okay? Now, why is that? Why does that occur? What is the driving factor behind that we've talked about already? Well, it's going to be the central limit theorem that we looked at previously. As the degrees of freedom gets larger, then we begin to have approach a normal distribution. So the other thing to be thinking about when we're looking at this is obviously we have a distribution is different for each degrees of freedom. And lastly, all our values are going to be 0 or positive. You cannot have a negative value for your chi-square critical value. So let's take a look at why that would be the case. So this means all these tests are always going to be right-tailed. And if you looked at the distribution table, you're going to see they are all right-tailed tests. Let's think our way through why that would be the case. If there was a large discrepancy between the observed and the obtained, we need to think about what we would get as our output. So, since we're using the obtained minus the expected squared, if the obtained and the expected are equal, then O minus E is going to equal what? Well, it's going to equal 0. And then if we square 0, we get 0. So that's the lowest possible number we can have. If 0 is greater than E, then O minus E is going to equal 1 or a higher value, right? And 1 squared equals 1, so it's going to make it a positive value. If the observed is less than E, then O minus E is going to equal a negative value, for example, a negative 1. And when we square that, we're still going to get the positive value of 1. So this is why anytime we're using a chi-square distribution table, 0 is going to be the lowest possible value that we can have, and they're going to be positive. So if you have done a chi-square distribution and you feel that you have a negative number, something somewhere has gone astray. You need to go back and recheck your data entry and work through your steps again. Okay, so what is necessary to locate my critical value for my chi-squared? So looking at that table, what are the things I need to have? Well, I'm going to need to know my alpha and my degrees of freedom. So when we're looking at this, my alpha is going to be 0.05, and my degrees of freedom is going to be k minus 1. So here we do not calculate degrees of freedom based on the number of the sample size, not n, but k, the number of categories. So here, k minus 1 gives me what for my degrees of freedom for this particular problem? It's going to give me a degrees of freedom of 9. So going and looking in your chi-square distribution table, go through and use it, locate your degrees of freedom of 9 along the left-hand column, and go over till you find your alpha 0.05. And what do you get there for your critical value for chi-squared? Well, you should be getting a value of 16.919. So that is our critical value for our chi-squared. So now we have these pieces. What's the next step we need to do for conducting a chi-square analysis with the critical value approach? Well, we're going to need to graph it. So now we're moving into graphing the problem. So if we look over here, I've started to set this up for us. So here's our distribution. Here we have our chi-squared critical value of 16.919. Now, is the rejection region going to be to the right or to the left of 16.919? The rejection region is going to be to the right, and the fail to reject is going to be to the left. So now I need to go in and plot on my chi-squared obtained value of 6.6. And is that going to be to the left of my chi-squared critical value or to the right of it? Well, it's going to be to the left. So here's my chi-squared obtained equaling 6.6. Which means, of course, I've got to assess my rejection region in this particular example. Are we going to reject the null, or are we going to fail to reject the null? Well, here we're going to fail to reject the null. So, we're reaching the end of this problem. What are my next steps that I have to complete? Well, I've got to restate the decision in the non-technical terms, and I've got to address our original claims. So here's our null and our alternative hypotheses again for us to work with. Again, make sure you're referencing those. So my final interpretation would be there is not sufficient evidence to support the claim that the samples from a population of heights in which the last digits do not occur with the same frequency. So when we're looking at this, pay attention to how this breaks down. So your opening sentence is either going to be there is sufficient evidence or not sufficient evidence. Okay? And then you'll be stating the claim that was positioned for you. So notice the specific claim that we have over here to the left, That's what follows next. So that's the claim that we're supporting or not supporting, right? Then we have a summing sentence. What does this mean for this particular problem? Thus, the data appear to be measured rather than just reported. So we have the opening sentence you always start out with here with sufficient or not sufficient evidence to support, and then you move into stating the claim you've been asked to address, and then finally presenting that back in terms of the overarching question the problem is asking, which is, are the heights actually measured or were they reported?